Okay, what we have here is the very last tutorial, and as we explained, there's no homework associated with this tutorial, and so this one's all about attendance. However, I will caution that this is a really good way to prepare for the torque portion of the final exam. And as I've mentioned before, a big part of that final exam is going to be on rotational dynamics, that's torque, and rotational kinematics, that was last week's tutorial, and fluids, which was the tutorial number 9. So let's go through this. We have a rigid bar, and it's free to rotate about its center, which is right there. And the axis of rotation of the bar is fixed in place, so it's got to rotate about that center of the bar. We have a force that's applied at point M, and the force is always at a right angle to the bar. As the bar turns, it stays at a right angle. Find the direction of the resulting angular acceleration by considering the resulting change in omega. Well, we start out with an initial omega that's 0. It's not turning. And we know that this thing's going to cause the bar to rotate counterclockwise. And that means, by right-hand rule, I'm going to have an omega that is out of the page. Okay, and if I look at those two things and ask, what do I have to add to nothing to get a vector out of the page, that means my change in omega has to be out of the page. And that means that alpha, which is just the change in omega divided by time, since time is always positive, these two vectors are always in the same direction. That means alpha is going to be out of the page. Now, we're asked to consider that maybe the bar was spinning at a constant rate before we applied that force. Does my answer above depend on whether the bar was spinning clockwise or counterclockwise? Well, let's consider those two cases separately. Let's first of all consider if it was spinning clockwise. Okay, if it were spinning clockwise, this force would slow it down. And so in that case, I would have an initial omega that was into the page by right-hand rule. And I make that big because let's say it's going fast. And then a little bit later, it's still rotating clockwise. I still have an omega into the page, but now it's smaller. It's slowed down. And so I ask myself, what kind of a vector do I have to add to a big vector in to get a small vector in? Well, that's going to give me a change in omega, which is out. And that means I'm going to have an alpha that is out. Well, now let's consider the case where it's counterclockwise. Well, if it's counterclockwise, then my initial is going to be out, and it's speeding up. This force would cause a counterclockwise rotation to speed up, and so now my final would be even bigger out. Well, again, that's a change in omega that is out of the page, and that means an alpha which is out of the page. Okay, so the answer to the question is no. It just doesn't matter whether it's spinning clockwise or counterclockwise or whether it starts from rest. Now, the definition of torque and the new right-hand rule for torque does that we find a position that goes from the pivot point out to where the force is applied. And what we do, we talked about this in class, is we reach from the pivot out along that position vector. And sometimes you just need to turn your page so that you're not reaching in an uncomfortable way and hurting your wrist. Just reach out to where the force is applied, and then turn your wrist so that you can wave in the direction of the force. Your thumb of your right hand is going to be in the direction of the torque, which in this case is out of the page. So the torque is going to be out of the page. And this is going to be by the right hand rule for torque. Does your answer depend on whether the bar is spinning clockwise or counterclockwise? Well, no. The right-hand rule has nothing to do with that. The rotation. Oh, can't write with the rotation. Okay, the relationship between the r vector and the f vector are always going to be the same, even as it's turning or rotating. Are the relative directions of the angular acceleration and the torque consistent with what you would expect? Yes. Torque causes angular acceleration. In class, we found that torque is equal to the moment of inertia times the angular acceleration. So they are in same direction. When? Always. Always. Just like linear acceleration always is the net force. How does your use of the right hand to determine the direction of torque compare to the use of your right hand to find the direction of omega? Well, not the same. Okay, so for omega, we curl fingers in direction of rotation. In the case of torque, we reach from pivot to force and turn wrist to wave in direction of force. So, very different. Now, in part C here, we're asked to compare the torque exerted by these forces on the same bar about the same pivot, the same axis of rotation, to this torque up here. Now, let's define this torque up here. We'll call this torque of part 1. And you can see that its magnitude is going to be r times f, and we said that its direction would be out of the page. Okay? So now if we look at we'll call this case A, and we see that the torque by the original force is going to be greater than the torque in case A, but in the same direction. Now, how do I know that? Well, because that torque is going to be equal to R times F times the sine of 135 degrees. And the sine of 135 degrees is less than 1, and so I'm going to get a smaller torque. Another way of thinking of it is it's only the part of the force that's perpendicular to the position vector that's going to be causing the angular acceleration that contributes to the torque. And so that's clearly smaller in this case. Now, in case B, we have zero torque because there's no lever arm. It's pulling in a direction that's not going to cause rotation about that pivot. Now, if we look at this last case, this is a little bit more complicated. We have this torque here is going to be 1/2 of the torque that we started with. I say that because the lever arm is only half as big, but it's still trying to make it go in the same direction. The torque would still be out of the page. So here I have twice the force, so this torque would be twice the torque of the original, but it would be out of the page. And so the torque of C is going to be, let's call out of the page positive and into the page negative. This would be 1/2 the original minus 2 times the original torque. And that's going to give me minus 3/2 the original torque. So the magnitude of this torque would be greater than the magnitude of the original, but the direction would be opposite. Okay, we're good with that page. Now, we're going to examine on this page two very useful shortcuts for finding the torque that is exerted by a force. And the first case says that we should, I'm looking for a straight edge here. Boy, and I'm not finding a good one. Okay, we'll use here we go. I've got a straight edge here. I'm going to come in here and I'm going to draw a line. So our original force, let's say, was that big. And call that F. Okay, and we're asked to give 3 examples of how we could exert a single force at the same point M that had a different magnitude than that of the original force in part A. Well, that's easy. Just any force that ends on that line I mean, I could come up with all sorts of these. I can come up with more than 3 examples. And you can see that I can't draw a straight line. Let me try that again. Okay. The important thing here is that in every case, we have the same position vector, r, from the pivot out to where the force is applied. And if our torque is r times F times the sine of theta, where theta is this angle between the direction of r and the direction of F, then if r is going to be the same for all of these, then in order to have the same torque, we'd better have the same F sine theta. And F sine theta we can call the perpendicular part of the force, or the part of the force that is perpendicular to the position vector. We'll call that F perp. Okay, so you see that even though F prime is greater than my original F, F perp is equal to my original F. And so I get the same torque. Here it says the magnitude of the torque resulting from a force F acting at a position R from a pivot point is given by this equation that we wrote. Both the torque and the position vector are the same for each case in part D. So this is the same, and this is the same. And what does this imply about the quantity F sine theta for each case? It must be the same. How is this reflected in your diagram? Well, all forces have the same F perp equals F sine theta. Okay. Now, here, so we call this, before we go on, we call this the useful force method. Okay? For this force, F prime, only part of it, the part that's perpendicular to the position vector, is going to be useful in causing rotation. The other part is just not going to cause rotation. Now, in this case, we have a balance beam, and that balance beam has its pivot right at the center of mass. And so what we've done is we've hung identical masses, identical objects at these two locations on the beam. Now, in this case, the force exerted is going to be the same. It's going to be equal to the weight of that object. But the position vectors, we'll call this F1 and this F2, and this we'll call R1, and this we'll call R2. And so we know that the force 1 is equal to force 2 because those are identical objects pulling the same amount. But we also know that R2 is greater than R1. And yet when we do this experiment, we find that the balance beam doesn't rotate. It doesn't move. It's balanced. And so if we look at our equation for torque again, and this time I'm going to write it as F R sine theta. If I define a line of action, which is a line that goes on forever along the direction that the force is applied, and we define a lever arm, which is the distance from the pivot out to the line of action and perpendicular to it. Well, remember, this angle theta is this angle between the direction of R and the direction of F, and that's going to make this angle theta. And so if I look at R sine theta, that's just going to be this lever arm. And so you see that in this case, I have the same force acting with the same lever arm on both sides. Okay, so it has no net torque, so it won't rotate. In part D, in position to remain constant, you found that the quantity F sine theta, not F itself, was important in determining the torque. In this case, part E, the force remains constant. Under these circumstances, what is the quantity analogous to F sine theta that determines the torque? Well, it would be the lever arm, which is R sine theta. Okay, so if the torque is force times R sine theta, then if this is the same for both cases, and this is the same, that means that this will be the same. Okay? And we call this the lever arm method. Well, great, Greg. You just gave me two methods in addition to the brute force method for solving a problem I really didn't want to solve in the first place. Why do I need so many methods? Well, you're going to find that, first of all, in 95% of the problems, this angle theta is 90 degrees, and it's just a force times a distance, where the force and the distance are perpendicular to each other. But in those 5% of cases where theta is not 90 degrees, there are some problems where the useful force method makes it trivial, and it's really hard to do it with the lever arm method. There are other problems, like this one here, where the lever arm method is very, very simple and makes the problem obvious, whereas the useful force method is not so simple. So it's good to have both of these methods in your toolbox so that you can use them when they are called for. Now, this third page of the tutorial is an easy one. This one is going to go quick. Okay. What we have is a meter stick, and we have a pivot that's right at the center of mass for that meter stick. And you're asked to predict the motion of the ruler after it's released by the hand there. And I'm not sure what you're going to predict, and it's too bad that you couldn't actually try this out or be in the in the room. But when the hand lets go, that meter stick doesn't go anywhere. Now, some of you are thinking, well, wait a minute, isn't it going to balance out? Isn't it going to go parallel to the floor? And the answer is no, because we put the pivot at the center of mass. With a balance beam, if I've got a balance beam, what I want to do is put the pivot above the center of mass. And if this is, say, connected to a pole, then the weight force is always going to apply at the center of mass of that balance beam. And if we rotate this beam, that's going to move that center of mass out from beneath the pivot. And we found in lecture that last Friday that center of mass is going to want to get back underneath that pivot, because that weight force is going to cause a torque. But if I put that pivot right at the center of mass, then the center of mass is always right at the pivot, and so you can't get a torque. So there's no motion results. Okay, so what is the direction of alpha, the angular acceleration of the ruler, about the pivot? Well, alpha is 0. It doesn't move. And that means that the net torque has to be 0. Okay, because the torque is what causes the angular acceleration. What's the direction of the acceleration of the ruler? And by here we mean the center of mass of the ruler. Okay? Well, the linear acceleration of the center of mass is 0. It's not going anywhere. Besides, it's pegged to that pivot. And that means that the net force has to be 0. Okay, because you remember, we decided that the net force is what causes the mass, the center of mass, to accelerate. Now, if we draw a free body diagram, an extended free body diagram, is the point where you place the gravitational force in your diagram consistent with your knowledge of the net torque about the pivot? Yeah, that weight force has to act at the center of mass. Otherwise, I'm going to get a torque, and hence an angular acceleration. And so the other force is going to be the normal force by the pivot on the meter stick. Okay. Now, how would your free body diagram change if the ruler had twice its original mass? Well, I would get twice the weight and twice the normal force by the pivot. But the net force is still 0, and the torque is still 0. Whoops, I'm sorry. The net force is 0 and the torque is 0. Okay, now this page is arguably the most important page of the whole tutorial. This one really kind of gets at some key ideas that you need to wrap your brain around. The ruler is initially at rest and horizontal, and then a student shoves the right end of that ruler down. And the magnitude of the force by the student is less than the weight. We're going to need that information in a little bit. Okay, so let's say the weight of that ruler is, I'm making this up, 5 newtons. The hand is pushing with something less than 5 newtons, let's say 3 newtons. And it's just a brief shove, and that gets the ruler spinning. And in time B, a little bit later, that ruler is spinning around at a constant rate after the hand has shoved it. So describe the rotational motion of the ruler during the time that the hand is pushing. Well, I started out with no rotation. I end up with rotation that's going to go clockwise, or an omega into the page. That's going to give me a change in omega. These are vectors. That is into the page, and that means I'm going to have an alpha that's into the page. If I look at an instant sometime after the hand has stopped pushing, I have an omega that's constant. That's going to give me an alpha of 0. Now what about the translational motion of the ruler? And by that I mean the motion of its center of mass. Well, initially it's not moving, and even though it's speeding up in a rotational way, the center of mass isn't speeding up, it's still 0. And so that means that the change in velocity of the center of mass is 0, and hence the acceleration of the center of mass is 0. Okay, and after you stop pushing, I've got the same argument. The center of mass isn't moving at any time or any later time. Okay, it's just not moving. Now, if I draw an extended free body diagram for the ruler during a moment when the hand is pushing and sometime after the hand has stopped pushing. Well, after the hand has stopped pushing, I'm going to have a weight force here. And we said that weight force, let's call it a ruler now instead of a meter stick. I'm tired of writing all the subscripts. Let's say that was 5 newtons. Okay? The only thing touching the ruler is the pivot, and it pushes with a normal force. And if the center of mass is not accelerating, then the net force has to equal 0. So this net force by the pivot on the ruler has to also be 5 newtons. Now let's go back to part A. I've got the weight force that I put at the center of mass, and we said that was 5 newtons. We have this normal force by the hand on the ruler, and we said that was 3 newtons. Now the only other thing touching the ruler besides the hand is the pivot, and it pushes with a normal force. It's going to be straight up. Now the question is, how big should I draw that force? Is that going to be 5 newtons or is that going to be 8 newtons? And the answer, and this is the big idea, this is the big takeaway from this page, is that Newton's second law for the acceleration of the center of mass doesn't care where the forces are applied. All the force up has to balance all the force down if there's no acceleration up or down. It doesn't matter whether some of the forces are out on the edge or some of the forces are acting at the center of mass. Remember back when we were doing linear dynamics, we didn't have to draw an extended free body diagram. We just drew the object as a dot, and that dot was representing the center of mass of the object. And it was our way of saying we just don't care where the forces were applied on the object. If there's no acceleration, all the force up balance all the force down, end of story. And all the force to the left balances all the force to the right. So that means that this normal force by the pivot on the ruler has to be 8 newtons. Okay? Because 5 plus 3 is equal to 8. And that gives me balance. All the force up is equal to all the force down. Now, here we're asked, and we need to rank all of our forces. So let's see. What's our biggest force? Well, our normal force by the pivot on R in case A is going to be the biggest. And then the second one is going to be the weight force in case A, which is equal to the weight force in case B, because they're identical meter sticks, and we said that that's equal to the normal force by the pivot on the ruler in case B, and that's got to be bigger than the normal by the hand on the ruler, because that's less than the weight given in the problem. Okay, what is the direction of the net torque about the pivot in each of the 2 instances? Well, in instance A, these 2 forces that act at the pivot give me no torque about the pivot. If I look at the torque exerted by the hand, I have to define a position vector R, and then I would turn my page so that I can reach in the direction from the pivot to where the force is applied, turn my wrist so that I can wave in the direction of that push by the hand, and that leaves my right thumb pointing into the page. So that would be, for case A, the torque would be into the page by right-hand rule for torque. Okay? And it's caused by the force by the hand. In case B, the torque is, and we're talking about net torque, is 0. Okay? The forces act only at the pivot. And so I've got into the page and 0. Which forces on your free body diagram have a non-zero contribution to the net torque? In other words, which ones give a contribution to the net torque? Well, only the force by the hand. All other forces act at the pivot. What is the direction of the net force on the ruler in each of the 2 instances shown? And that's just 0. The center of mass never accelerates, and so in both cases, when the hand's pushing or when it's not pushing, I have balance or 0 net force. Which forces on your free body diagram have a non-zero contribution to the net force? Well, all of them. Okay? For F net equals MA, all forces go in here. Okay? And part D is just asking us, are our descriptions of the motion in part A consistent with our answers to B and C? And yeah, we did it right. We did it right. Okay. Okay, now let's go on We have two students, student 1 and student 2, and what we're going to find is that it's really student 1A and student 1B. They're both student 1. And student 1 says, while the hand is pushing on the ruler is speeding up. This means that the ruler is accelerating. By Newton's second law, F net equals ma, the ruler must have a non-zero net force. So student number 1 is making the mistake of not recognizing that F net equals ma only applies to the center of mass. Which does not accelerate. Okay. Now student 2 says, while the student is pushing on one end of the ruler, the center of the ruler does not move. This means that the two forces exerted at the center, the weight and the normal force, have the same magnitude. Well, we know that's not right, because in that case, the weight had a magnitude of 5 newtons, and the normal force by the pivot had a magnitude of 8 newtons. So those are not the same. So what this person is not realizing is that F net equals 0 gives the normal by the pivot on the ruler has to equal the weight of the ruler plus the normal by the hand on the ruler. Okay, all the force up has to balance all the force down. And here we just check our answers. Okay, we're almost done. In this last part, we have a little exercise where we have 2 spools, and those spools have thread wrapped around them. In case A, it becomes very important. In case B, it's just so that it's got the same setup as spool A. So we tie the thread from A to the ceiling in such a way that that string is hanging perpendicular to the ceiling, or vertically. Okay? And then we put X's below the center of mass of each of those spools on the floor. Now, if we draw an extended free body diagram for each spool, an instant after they are released but before they hit the ground. If I look at spool A, I have a weight force that I always put at the center of mass. And then I have this tension force by the string on A. Now I drew that tension force smaller than the weight. How do I know that it's smaller than the weight? Well, I know because A is going to accelerate down. Okay? And that means it needs to have a net force down, and this force by the tension should be vertical, and this force by weight should be vertical. Now, if I draw a free body diagram, an extended free body diagram for B, I only have the one force, the weight force. Okay? Now, for each spool, find the direction of the net torque about the center of the spool. Well, the net torque on A is going to be out of the page. And whoops. Okay, turn the light back on. This is caused by the tension force by the string on A. Okay, and this would be the lever arm, Also the position vector. In this case, the lever arm and the position vector are the same. In the case B, the net torque on B is 0. And that's because the only force on the spool acts at the center of mass. Okay, now let's think about that experiment for a little bit. I'm going to put that right up here so we can still see it as we answer some of these questions. We are supposed to predict which spool will reach the floor first. Which one do you think will reach the floor first? Second question. Will spool A strike the floor to the left of the X, to the right of the X, or fall straight down and hit the X? How can you use the free body diagram to answer this question? And was it important to consider the spool as an extended object in order to make your predictions? If we just want to know the linear acceleration of the center of mass of these spools, we didn't need to draw an extended free body diagram. So we do not need an extended free body diagram. And if I draw a regular free body diagram for A, I've got weight down and the tension up. If I do the same thing for B, I just have the weight down. Now, the magnitude of the center of mass acceleration is going to be bigger for spool A. Why? Because the net force is greater. Oh, I made a mistake. Look at those two free body diagrams. Which one has the greater net force? The answer is going to be this way. Okay, so let's pretend that I just didn't have that senior moment. The acceleration of the center of mass of A is going to be smaller than the acceleration of the center of mass in case B. That's because the net force on A is smaller than the net force on B. Okay, I'm going to make up some numbers here. Let's say that the weight of the spool is 15 newtons in both cases. And the tension in that string is, say, 6 newtons. Well, the net force on A is going to be 15 newtons down plus 6 newtons up. Well, that's when you add things in the opposite direction, you're really subtracting them. And so that's going to be 9 newtons down. Whereas the net force on B is just going to be the 15 newtons down. I got a bigger net force on B, so it's going to hit the ground first. How about the direction of the center of mass acceleration of spool A compared to that of spool B? They're the same. There are no horizontal forces. Okay? So that means that both of them are going to go straight down. They're going to hit the X's that are below them, and it's just that B is going to land first. Below is an incorrect statement about spool A. The string exerts a force that is tangent to the rim of spool A. This force has no component that points towards the center of the spool, so this force does not affect the acceleration of the center of mass. F net equals MA governs the motion of the center of mass. And this involves all the forces, regardless of where they act. That's why we only needed a dot. when we were back doing linear dynamics. Now, we don't need to do this part of the tutorial. We're gonna just skip that part there. Okay? So I hope this has been helpful. I'm sorry for the mistakes that I make. Just chalk it up to being an old man with a faulty brain, and I hope you're getting this stuff.